Okay, so it's a great pleasure for us to have Annalisa Bracco today. So Annalisa is from the School of Earth and Atmospheric Science at Georgia Tech. So Annalisa is a specialist of ocean dynamics and climate. So she has made many things, studying ocean mesoscale dynamics, the role of coherent structure and their mixing property, the study of vertical mixing at mesoscale, and how ocean and interannual and decadal scales affect climate. So she obtained several awards, including an AMS Niklas Fofonov Award in 2001. So it's really nice to have you today, Annalisa. So Annalisa will speak about analyzing changes in the tropical Indo-Pacific in the last 60,000 years.
Thank you. Thank you, Freddie. I'm going to, I guess, share my screen. Let's see. And now if I put this in presenter mode, it should work. Ta-da. Okay, can you all see it?
Yes.
Okay, perfect. And please ask any question during the talk. So I'm going to present some work we have done. So Fabrizio Falasca was a graduate student with me at the time, together with Pascal Braconneau and Julien Crétat. He had a fellowship to go at APSL for 3 months and worked on this, on analyzing this very long run that it's, and the interest was in figuring out ways to identify climate shift. And in this talk, I'm going to focus on the tropics, where we really didn't see any abrupt shift, at least in this model, but where we can look at the evolution of the climate system and the tropical interconnections over 6,000 years. And I'm going to do that using a machine learning unsupervised network approach. See if I can. Okay, so the objective is really to find a way that allow us to look for changes in dynamics and connectivity pattern in climate fields and identify the modes of variability in an independent way. So whenever we have a model and we are going in the past and the climate modes of variability may be different from the one we know today, can we just use a machine learning tool to identify them automatically? And then how can we figure out what is the connectivity structure among those modes of variability and how they are evolving in time? So what we did has been to develop a network system, a machine learning network, complex network method that identifies domains in any kind of data set you want to use. And it looks for how those domains evolve in time eventually. And domains are spatially contiguous regions. They may be overlapping, and they have to be homogeneous to the underlying variable. So if I'm starting from SSTs, for example, the dynamics, so the time evolution of the SSTs among grid cells that belong to the same domain have to be very strongly correlated. And we have developed that with Konstantin Dobroli's here in the College of Computing. It's the 2018 paper by Ilias Foutalis et al. And then Fabrizio Falasca used and modified the code and to investigate variability in CSM large ensemble to begin with. Once you have, and I'm going to use this method, so that's why I'm introducing here, but then I will use it in a slightly different way from the way I'm then applying it directly on the variables of sea surface temperature per se. Once we have those domains, we can infer a network. And what that means is that each domain will be connected to other domains, and there will be a link that will capture how strong is the covariance of the interactions between two different domains. And this covariance and those links can also be lagged. So we also managed to capture the temporal ordering of the interaction. So what you see here is an example using Hadley SSTs, where the strongest domain is the one indicated by E, which essentially corresponds to ENSO. And we can start from that and find that actually there is a lag at 8 months, which is prior to ENSO, which is coming from the tropical Atlantic to the south of the equator, that is influencing ENSO dynamics. And it turns out that this has also been studying, and it's associated with a propagation of Rossby waves in the atmosphere. And then the ENSO domain is influencing other regions in the planet, of course. And it's quite strongly influencing, for example, the Indian Ocean, the IO domain in this case, and is almost a simultaneous interaction. As you can see, there is no lag there and there is no arrow. So essentially the time zero lag at monthly time scale, it's included in the maximum possible correlations. And so we can exploit this tool to really look at how different domains emerge, and you can do this in the models, or you can do this in the observations, and then how those domains are linked with each other.
Annalisa, may I ask you, here the domains are defined, the spatial domains are defined once for all? And you look at the signal in each of these domains?
So in this case, the answer is yes, and this was done over 50 years. You can also do it with, so that's exactly the problem I'm going to discuss when I'm going to 6,000 years, because at that point I cannot just have domains that are fixed in the same way. In this specific case, yes, we were considering 50 years and we have not changed the domain. It's very easy to do it with monthly mean, with a, like, change the, we do it on smaller, shorter timescales, and you just shift by like 3 years, for example, and you recompute the domains as well.
And then you have an index for each domain, for instance, the sea surface temperature or something?
Yes, yes. In this case, yes. So you're going to have an index for whichever field you're considering up to this point.
Thank you.
So this is just an example. Here we were looking at CSM, at the large ensemble of CSM, and we were looking at the evolution of the ENSO domain in the 2100. So for about 130 years. And what you can see there are all the various members and how the evolution changes among the members. And what I'm plotting is also the ensemble mean, and the in black on the top, and the sigma, plus minus 1 sigma. And what you see in the plot on the top is also the signal for the Hadley SST and from Kobe. So first of all, the two analyses are not identical. Second of all, the Hadley SST is always below the sigma, the 1 sigma interval of the CSM ensemble, but that's not the case for Kobe, for example, especially in the there is not a lot of agreement between, or at least there are some difference between the two analyses, especially before the 1990s, and then they are much more closer together. And what you see at the bottom is the evolution of the tropical mean strength. So we're taking the tropics, we're looking at the overall strength of the domain in that region, and we're looking at how that is evolving. over time, and of course is going to be dominated by the ENSO domain. And at that point, or whether there is a better agreement among the reanalysis, and the other thing that you can see is that the model, no matter which ensemble member we are considering, tends to overestimate what is the tropical mean strength. So essentially the tropics in this model tend to are a little bit overpowered. They're just overpowering the whole dynamics.
So what is the tropical mean strength? It's the strength of what?
Of all the domains, the mean strength of all the domains contained in the tropical band for this specific model, which of course it's strongly linked to what the strength of ENSO is, but is also considering the Indian Ocean and the tropical Atlantic. So it's just taking the mean of that. And the strength is defined as essentially the sum of the links between one domain and all the others. And so the more the more the domain, so ENSO is going to be your dominant one because it is the mode of variability that exerts the largest amount of teleconnections, essentially. So we can identify those patterns with this machine learning tool, and we can use links to look at their underlying connectivity structure. Now, how can we use this to identify regime transitions in space and time? And so look for much longer time scale where those connectivity may change. So the approach we are proposing is to move to the entropy field. And so we are going to consider a time series, which is embedded in a 2D grid, the same as we did so far. But we are looking at changes in information entropy. And we are quantifying the shifts in the dynamics of the time series by looking at the information entropy changes. So for every time series, we consider a time window. In our case, because we're going to look at 6,000 years, our time window is going to be relatively large. It's going to be 100 years. And we compute the information entropy over this time window, which is essentially we're following the definition presented by Corso et al. In 2018, and we are essentially looking at the recurrence plot for the computation of the entropy. Then we repeat the same operation every 20 years. So we are shifting our interval, and we're doing the 20 years, the first 100, and then 20 to 120, 119, and so on. And this is giving us a complexity field, which has both a spatial and a temporal variability, essentially. Now on this field,
what will be the time series? What will be the X here?
So we are going to have we are going to compute the recurrence plot. So our time series is, we're going to take the time series 100 years. We are going to compute the entropy on that 100 years. I will start doing that on sea surface temperature. And I'm going to have a field that is representative of those 100 years. Then I'm going to shift, and I'm going to have a different field, which is going to be representative of my 20 to 120 years and so on. And I can build the time series for each grid point, looking at how the entropy is changing at intervals of 20 years. And now on this new field, I can build a network using delta maps, the one that I showed you before. And I can build therefore a network based on the entropy time series at each grid point. And those entropy time series now have less points than the one I started with, because I essentially have only 1 point every 20 years. So I'm going to infer the network, which is still going to be weighted, may have a direction, may be time dependent, and is going to be between regions that are homogeneous in their time evolution, but they are homogeneous in their time evolution in the entropy space, not anymore in just the sea surface temperature space. And so they are going to give me an idea of when that entropy is shifting significantly, and therefore when I may have a climate shift. The reason to go into the entropy, beside the fact that it's an interesting quantity, it's because we are trying to look at a simulation which is 6,000 years old and 6,000 years long. And so it's a huge amount of data, and is what we're interested is the evolution of the climate system and possible climate shift along this whole period. What this model has, so this model started 6,000 years before present, when present is 1950. It has, is considering changes in greenhouse gases, but the changes are very, very small until the last 50 years, and is considering changes in insolation, which are instead more significant. It's a 1 degree model in the atmosphere, 2 degree ocean model. It has sea ice, and it has an interactive land surface. And it's coupled with biogeochemical cycles, both over ocean, over land, and it has a dynamical vegetation. So we are going to look at how this model is representing today's climate as first thing, just to show you that, and we're focusing in this specific, we have done a global analysis, and we actually found that there are abrupt shifts at high latitudes, especially in the Southern Ocean. However, in this talk, I'm concentrating on the tropics. And what you see here, it's how this model is representing today tropical climate in the Pacific and in Indian Ocean. So the top is the first UF. So what you would expect is to see ENSO. You do, but the pattern is not perfect by any means. There is less load than expected in the Central Pacific, and the pattern extends too much into the warm pool. In terms of Indian Ocean, what you see is again Kobe on top and IPSL, the model at the bottom, and those are the first two EOF. The first mode is the general warming that it's associated today is strongly linked to ENSO. And you see that the model does a decent job, except for that area of blue, which is likely linked to the extension of ENSO in the Pacific, which is just too much, getting too much into the western side of the domain. However, you also see that the model is, the variance explained by the first EOF is quite a bit smaller in the model than in the observation for the Indian Ocean. And then the model, so that's the what is called usually IOB, Indian Ocean Basin mode. So it's doing the right pattern, it's not necessarily doing the right, the variance explained is less for the model. It's doing a pretty good job with the IOD, so the dipole, that is the second mode in the Indian Ocean, both in terms of pattern and in terms of variance explained. So we at least have an idea that the model is doing something quite reasonable as far as today goes. Here we are looking at the sea surface temperature anomalies, and we are computing the entropy every 400 years, every 20 years. And what I'm showing here is the mean over time complexity field, so entropy field average over the whole period. And of course, we do a similar map, and we can look at the evolution of this field through the 6,000 years for every 20. So what you can see is that the entropy is very high in the Indian Ocean, it's very high in the tropical Atlantics. Interestingly enough, if you look at today climate, the tropical Atlantic does not emerge, at least in the analysis, as a region of high entropy, but the Indian Ocean does. And then ENSO is a region in the tropics of low entropy because there is a regularity into it, with a greater entropy in the upwelling region and in the also eastern boundary upwelling systems. But especially in the cold tongue, you can see that the entropy is quite significantly higher, and that's true also for the observation. You do see very clearly here the double ITCZ emerging even in the entropy of the SSTs, actually, which is again a problem that this model has.
Annalisa, how do you interpret this entropy? You seem to relate it to variability or something?
Yes, because
this interpretation
essentially is quantifying what is the recurrence at a given grid point. So it's essentially linked to the predictability of that grid point, of the variability at that grid point. If you have something which is periodic, the entropy is essentially going to be 0 if it's a perfectly periodic.
Mm-hmm. Okay.
Because it's just going to recur continuously with the same distribution.
So the more the entropy, the larger is the entropy, the more chaotic is the dynamics.
Correct. Correct. So ENSO does emerge as a not so chaotic mode, obviously, because there is some recurrence into it, and that's true also for the observation. This map we calculated for just the last 50 years, and it's not significantly different in the observation except for the Atlantic, and for the fact that the shape of ENSO is slightly different. But it's the difference between the Central Pacific and the cold tongue. It's also in the observations. So now we can build domain on this complexity field. And what you see here are the domain that emerge from the field that I've shown you here. And then we can build indices that evaluate how those domains are evolving based on their entropy, essentially. And so we can have a domain complexity signal, which is essentially given by the formula below, where A is a name for a generic domain. And we are summing the entropy value over all grid points that enter in that domain A. So this is what happened for ENSO if you do that. And so here we are inferring a functional network every over 50 years and doing that with a running mean of 3 years. In this specific plot, the time has not been reversed. And so 0 is the mid-Holocene and 6,000 is 1950. And what you can see is that overall the complexity of ENSO has increased for time and then kind of stabilized in the last couple of thousand years, with some larger values seen in the last couple of hundred. However, not something which was not seen before. So you can also find values that are comparably high in around 3,000 years ago, in the middle of our time period.
So the domain are fixed in this plot?
Yes.
So you
And
interpret
it's essentially the domain infer here, which is based infer on the entropy field, on the mean entropy field.
So shall we interpret the plot here as ENSO being more predictable in the last part of the time series?
If you definitely in the first part, it was more predictable.
Okay.
It was also, so this was also the strength of those domains. So what is also telling you is that it was exerting less of an influence. Then the influence became stronger and it became a little bit less predictable. And then it went back to be slightly more, I mean, it's hard to see that, you know, those three lines are kind of done by eye. There is not a very good reason to separate them in those three periods. There are some reasons, but not necessarily proven. And what you see is that the last couple of thousand years have been pretty regular, like the strength has not changed dramatically and the level of chaoticity has not changed dramatically, except for the last couple of 100 years, where you really see a spike. However, this spike is not unprecedented because it's at least as large as the one at 2,500 years ago. Where we're looking at coral records, we do see something that may be comparable in terms of strengthening over time. However, we don't seem to have the same kind of spikiness right here around 2,000 years ago. However, it's also the period for which we have the least number of reconstruction, because we are essentially in this area where we only have a couple of points. Actually, one really. So considering the fact that we have so few observations from corals, reconstruction from corals at this time, what we are seeing, it's consistent with what the corals have been, or other proxies have been saying. Which is good, I guess, but it's also hard to really test completely this variability. This is the only example that we found, was published in 2019, where this there is a 4,200 kilo event, 4.2 kilo event, clear event that may have changed and may have caused an increase in strength in ENSO and higher variability in ENSO, which may correspond to what we are seeing here in the central at like what in my x-axis is about 3,800. So we're kind of happy with the model in the sense that it's doing a variability that, when it's compared to what the records, the paleo records are saying, seems to make sense. It's at least consistent. It's not completely off. So how is that looking in terms of teleconnections? And so what is the overall dynamics that is ongoing in the Indo-Pacific? And this is what, this is really the main plot of this talk. Here I'm considering the ENSO domain and its evolution in terms of its sigma over time. So the strength of that domain and how the sigma is evolving. And then I'm also considering the two Indian Ocean domains that emerge from the entropy signal. And what you see is quite a significant decrease in the Eastern Indian Ocean sigma, and kind of a constant instead Western Indian Ocean domain. And again, in terms of their variance and their strength, the variance of their strength. And what you see on your right, so those four curves that are on the top are the correlation between the variability in entropy in ENSO and Eastern Indian Ocean, which is in black, which is small at the beginning and kind of increasing towards today. With the correlation between the Western and Eastern Indian Ocean actually changing sign between the first couple of thousand years and the last period. And with the top is ENSO, well, ENSO and the Western Indian Ocean remain strongly correlated over the whole time. So the correlation between ENSO and the Western Indian Ocean is simply an atmospheric teleconnection. And this is it's the well-known teleconnection that caused the basin mode and the warming in the Western Indian Ocean whenever you have an El Nino in the Pacific, and vice versa. So what you see here is that that teleconnection has been there all the time. But the relationship between the Eastern Indian Ocean and the Pacific has changed through those 6,000 years. And what you see at the bottom of this figure is the time lag of those correlations and the strength of those connections between those three domains. And what you can see is that the correlation has intensified. So ENSO has been exerting a larger role in impacting the dynamics over the Indian Ocean. So in the last 2,000 years compared to the first two. And the other thing that you see is that the lag of those correlations has shortened a little bit and has become more, the color of those arrows it's giving you the strength of the correlations. And also we have a very strong correlation between the Western and Eastern Indian Ocean, which is essentially given by the dipole, which we didn't have, or we had in an opposite sign at the beginning. So we have changed significantly what's going on, the dynamics in the Indian Ocean through changing the ENSO teleconnections. So what were the mid-Holocene conditions in terms of El Niños and in terms of modes of variability in the Indian Ocean? Here I simply UF done on the first 100 years and the last 100 years of the simulation. What you can see is an intensification of ENSO very clearly, and also a change much more radical in a way in the Indian Ocean, where the first UF was the dipole. And it becomes the Indian Ocean basin mode. And the second UF was the Indian Ocean basin mode, and today becomes a dipole, which have, however, a loading which is not at the equator, but is further south, which is observed. So it's in agreement, it's in better agreement with the observation. What you see at the beginning of the period we are considering is actually a dipole which is very strongly equatorially linked. It's stuck on the equator, and has been also called equatorial mode to differentiate it from the dipole, which has greater load further to the south. Here it's essentially the evolution in three quantities: surface temperature, vertical pressure, and precipitation. And this is simply the reference on the top, so the first 500 years, and then at intervals of 500 years, the difference. And so you can see a general warming that happened through the 6,000 years, and a general intensification of the pressure system that is associated with ENSO and with the warming in the Indian Ocean, which is a subsidence into the Indian Ocean. And you can also see a significant change in precipitation, with a signal in precipitation that intensify in the warm pool and strongly changes the precipitation variability in the Indian Ocean, drawing very clearly the western side of the domain and the Arabian Sea. We can also look at this evolution through a nonlinear dynamical approach. So what here we are looking at taking the 5 variables, surface temperature, pressure, U and V at 850 hectopascal, and precipitation, and encoding the annual value of those variables in one point, and then looking at the evolution of that through a PC decomposition. So the explained variance that you see is not a lot to the first 3 components, but what is very clear is that the system is changing his state. So its mean state is evolving, and with it is actually also changing the variability. But here you can just see the evolution of the system in a phase space, essentially representation using a PC decomposition. So it's essentially the attractor of this whole system at annual scale, and how that attractor is evolving. And then we can take this representation and we can look at the first 3 PCs, and we can project them and look at what the pattern is of the changes associated with this attractor. And what you see is really an intensification of ENSO in the model in terms of surface temperature, in terms of subsidence, vertical velocity, and in terms of U, V, and precipitation. So what we're really seeing is an intensification of the Walker circulation, it's the strengthening of the Walker circulation, which changes the teleconnections between the Pacific and the Indian Ocean, and that it's consistent also co-occur with the weakening of the monsoon at the same time. So essentially, we have presented a framework that allows to investigate for regime shifts, and we can do that in space and in time. We found non-linear regime shift in SSTs, but they were in the Southern Ocean, and they were only confined to high latitudes. We found that we can use a climate network in time to look for trends and variability in the climate connectivity. And we can do that using multiple fields simultaneously. And then in terms of the Indo-Pacific, which is really what I presented today, we can see that the mean state as slow changes that set the stage for quite a larger shift in variability by strengthening the El Niño standard oscillation, but especially by making the Indian Ocean basin mode the dominant one. So in the mid-Holocene, the SST gradient in the equatorial Indian Ocean was favoring an equatorial dipole, which was independent of ENSO and was similar in its dynamics to what we see in the Pacific and probably closer to what we see in the Atlantic, so the Atlantic Niño. And those dynamics have been found to be relevant by Timuraitai et al. And Dinezio in the CSM model of the latest generation for future climate. So if you continue warming at the end of 2100, Dinezio et al. Found that you may go back to an equatorial dipole mode in the Indian Ocean. And Tirumalai et al. Found this equatorial dipole mode looking at the last glacial maximum. And this was a simulation just of the last glacial maximum. And they were finding that the Indian Ocean had this dipole mode shift, which was really dominating the dynamics. And what we seem to find with this model is that the same condition were there all the way into the mid-Holocene and then slowly changed into what we observe today. And the spatial signature of the mean state changes are a warming, persistent warming of the tropical Pacific and of the Indian Ocean, a weakening of the Indo-Asian monsoon, and a strong strengthening of the water circulation that essentially change the teleconnections in the overall. And this is it. And this is Fabrizio, who did all of this analysis as part of his PhD thesis.
Thanks a lot, Annalisa. Yes, yes. This was a very nice talk. It's a very interesting way to analyze the dynamics through this domain used from the entropy. So do we have a question for Annalisa? So I was very interested by your picture where you see the strength of the link and the correlation between ENSO and this one. So what is the meaning of the percentage here you have on the triangles?
So we are considering when that link is present in all those 3 years network that we are building every 3 years, right? So what this is telling you is that in each of the network, so in 86% of the network that we build for this 6,000 year divided by 3, that link is present with, on average, that lag. And so the link between ENSO and the Eastern Indian Ocean was pretty weak because it was essentially non-significant. Mm-hmm. And it was not even present all the time at the beginning. And then it becomes a link which is significant, statistically significant and present at pretty much 99% of all the networks that we build. So essentially at all the time in the last 2,000 years.
Okay.
So so we are just, we are focusing on that specific link and saying, do we find that link all the time in all the networks that we're building? And the answer is no. And so we measure what is the percentage in which we find it. And of course, the weaker is the link, the less likely it's going to be to find it.
It's also striking that the sign of the relation between the West Indian Ocean and the East Indian Ocean is changing.
Well, if you think of because in the first 2,000 years, we essentially had this dipole mode, right? This equatorial mode, which is really an El Nino, like it's the same dynamics. So it's internal to the Indian Ocean. And it's really something that starts with oceanic upwelling of Java and Sumatra and moves. And then you have Rossby waves that are transporting the signal. So essentially it's something that you see also if you take a couple model and you close completely the Indonesian through flow, these modes reappear. And it's really the eastern upwelling that drives then the warming in the west. Well, if you look at what we see today, it's often, we still call it a dipole, but it's very hard to find what is coming first or later because everything is really pretty quick. And part of the reason is that you do have the upwelling in the Eastern Indian Ocean, but you also have the warming. And so it's building up because they remain connected. So that's what caused this sign to change, essentially. It's not really changing, it's going to zero. You kind of see simultaneously the cooling and the warming today. And you used to see first the cooling and then the warming, essentially, in the past.
Do we have more questions for Annalisa? Okay, so thanks a lot. I think it was really a great talk.
Thank you. Can stop sharing.